There are 3 doors. Behind one of them is a car. Behind the other 2, goats. You pick door number 1. The host, who knows what's behind every door, opens door number 3. It's a goat. He turns to you. Do you want to switch to door number 2? Most people say it doesn't matter. Most people are wrong. And the reason they're wrong started a war. This is the Monty Hall problem, named after the host of the American game show Let's Make a Deal. It was posed to Marilyn Vos Savant in her Parade magazine column in 1990. A reader named Craig Whitaker asked the question, and Vos Savant answered, "You should always switch. Switching gives you a 2/3 chance of winning. Staying gives you 1/3. The response was extraordinary. Nearly 1,000 PhD holders wrote in to tell her she was wrong. Professors of mathematics, statisticians, people who taught probability for a living. They were furious. They were confident. And they were completely, spectacularly incorrect. Let's see why. The naive argument goes like this. After the host opens a door, there are 2 doors left. The car is behind one of them. Therefore, it's 50-50. Switching doesn't help. This argument feels airtight. It is also completely wrong, because it ignores the single most important detail in the problem. The host knows where the car is. He didn't open a random door. He deliberately chose a door with a goat behind it. That deliberate choice changes everything. When you picked your door, you had a 1 in 3 chance of being right. That means there was a 2/3 chance the car was behind one of the other 2 doors. The host then opens one of those 2 doors and shows you a goat. But the 2/3 probability doesn't vanish. It concentrates. All of it. Onto the one remaining door. Your door is still 1/3. The other door is now 2/3. Switching doubles your chances. Still not convinced? Let's make it obvious. Imagine 100 doors. 1 car. 99 goats. You pick door number 1. The host, who knows everything, opens 98 doors, all revealing goats. He leaves 1 door closed. Door number 47, let's say. Now, your original pick had a 1 in 100 chance of being right. That means there was a 99 in 100 chance the car was somewhere among the other 99 doors. The host just eliminated 98 of those doors for you. All that probability, 99%, is now sitting behind door 47. Would you switch? Of course you'd switch. The 3-door version works exactly the same way. The numbers are just less dramatic. Let's enumerate every possibility. No probability theory required. Just counting. Suppose the car is behind door 1. If you pick door 1 and switch, you lose. If you pick door 2 and switch, the host must open door 3, and you switch to door 1. You win. If you pick door 3 and switch, the host must open door 2, and you switch to door 1. You win. Now suppose the car is behind door 2. Same logic. Pick 1, switch, win. Pick 2, switch, lose. Pick 3, switch, win. And if the car is behind door 3, pick 1, switch, win. Pick 2, switch, win. Pick 3, switch, lose. 9 equally likely scenarios. Switching wins in 6 of them. Staying wins in 3. 6 out of 9 is 2/3. 3 out of 9 is 1/3. No tricks. No Bayesian wizardry. Just counting to 9. But let's do the Bayesian wizardry anyway, because it's beautiful. Bayes' theorem says the probability of event A given event B equals the probability of B given A, times the probability of A, divided by the probability of B. Let's define our events. You pick door 1. The host opens door 3, showing a goat. We want, what is the probability the car is behind door 2, given that the host opened door 3. If the car is behind door 2, the host must open door 3. He has no choice. That probability is 1. If the car is behind door 1, the host can open either door 2 or door 3. He picks at random. That probability is 1/2. If the car is behind door 3, the host cannot open door 3. That probability is 0. Prior probabilities. Each door has a 1/3 chance. By Bayes' theorem, the probability of door 2 given that the host opened door 3 equals 1 times 1/3, divided by the total probability of the host opening door 3. That total is 1 times 1/3, plus 1/2 times 1/3, plus 0 times 1/3. Which is 1/3 plus 1/6. Which is 1/2. So the answer is 1/3 divided by 1/2. Which is 2/3. The car is behind door 2 with probability 2/3. Switch. When Vos Savant published her answer, the backlash was immediate. Roughly 10,000 letters arrived. The overwhelming majority said she was wrong. A professor from Georgetown wrote, "You are the goat." A mathematician from George Mason University wrote, "You made a mistake, but look at the positive side." If all those PhDs were wrong, the country would be in very serious trouble. They were wrong. The country was fine. Paul Erdos, one of the greatest mathematicians of the 20th century, refused to believe the correct answer until he was shown a computer simulation. He saw the results, paused, and finally accepted it. The problem wasn't that these were stupid people. The problem was that human intuition about conditional probability is catastrophically bad. We don't process the host's knowledge correctly. We see 2 doors and our brain screams 50-50, because that's how symmetry works in our everyday experience. But the host broke the symmetry when he chose which door to open. And our brains refuse to notice. Don't trust the maths. Trust the computer. We'll run the Monty Hall game 10,000 times. Strategy 1. Always stay. Strategy 2. Always switch. In 10,000 games where the player always stays, the player wins roughly 3,300 times. 1/3. In 10,000 games where the player always switches, the player wins roughly 6,700 times. 2/3. Every single time you run this simulation, you get the same result. It doesn't matter whether you run it 10,000 times, 100,000 times, or 1,000,000 times. Switch wins twice as often as stay. This is not a theoretical argument. This is what actually happens when you play the game. So why does the wrong answer feel so right? 3 cognitive biases conspire against you. First, the equiprobability bias. When we see 2 options, we default to 50-50, even when the options were not created equally. The 2 remaining doors look symmetric, but they were not chosen symmetrically. Second, the endowment effect. Once you've picked a door, you feel ownership over it. Switching feels like giving something up, and losses loom larger than gains. You'd rather keep your door and lose than switch and feel like you threw away a winner. Third, omission bias. If you stay and lose, it feels like bad luck. If you switch and lose, it feels like a bad decision. People would rather be passively wrong than actively wrong. So even when the maths is clear, even when the simulation is clear, switching still feels wrong. And that feeling is exactly why the problem is famous. Now for the fine print. The Monty Hall problem has several assumptions that are often unstated, and if you change them, the answer changes too. Assumption 1. The host always opens a door with a goat. If the host sometimes opens the door with the car, the analysis breaks. Assumption 2. The host knows where the car is. If the host opens a door at random and happens to reveal a goat, then it actually is 50-50. This is the key distinction. A knowing host transfers information. A random host does not. Assumption 3. The host always offers the switch. If the host only offers a switch when you've picked the car, then switching always loses. Assumption 4. You have no prior information about which door the car is behind. The standard problem assumes uniform priors. Every assumption matters. Most of the genuine disagreements among mathematicians were actually about which assumptions were implicit in the problem, not about the mathematics itself. The Monty Hall problem is not really about doors and goats. It's about information. When you pick a door, you create two groups, your door, with a 1/3 chance, and everything else, with a 2/3 chance. The host then gives you free information about the everything else group. He tells you where the car is not. And every door he eliminates makes the remaining door stronger. This is conditional probability in action. The probability of an event changes when you learn new information. Not because reality changes, but because your knowledge changes. The car hasn't moved. Your information about where it is has moved. This same principle underpins medical testing, courtroom evidence, spam filters, and machine learning. Every time an algorithm updates its beliefs based on new data, it is doing exactly what the Monty Hall problem illustrates. Bayes' theorem is the engine of rational belief revision. And the Monty Hall problem is the simplest possible example of why your intuitions about it are wrong. 3 doors. 1 car. 2 goats. A host who knows the truth. Pick a door. Watch him reveal a goat. And switch. Always switch. Not because it feels right. It doesn't. Not because it's obvious. It isn't. But because the maths is the maths, the simulation is the simulation, and 2/3 is more than 1/3. Nearly 1,000 PhDs learned that the hard way. Paul Erdos learned it from a computer. And now you know it too. The debate is over. Switch.